Hi everyone, let us discuss Gauss Divergence Theorem for a cubical region. Okay, so here we have a cube of side A. You can easily see this cube we have, and F is a vector field which is defined on the surfaces of that cube. And we have to prove that the value of this surface integral is equal to value of this volume integral. So divergence of F bar we have to find, and we have to calculate this value volume integral over the volume V. V is the volume of that cube and S is the surface of that cube. So we have to prove simply this left hand side is equal to right hand side. First of all, we will start to work on left hand side. That means we will find the value of that surface integral first. So as you can see here, S, that surface S is a surface of cube, which is clearly made up of 6 different surfaces. So let me mention all those 6 different surfaces. So S is made up of S1, S2, S3, S4, S5 and S6. Okay. So what is S1 I will consider? I will consider this ABGD. So this is ABGD, which is on the front side of this cube, and exactly opposite to S1 there is a S2 on the back side of that cube. So it is EFCO. You can easily see EFCO. So that is a S2. So this is S3. Okay, this is S3 I will consider, that is CFGB. This is S3, and exactly back side of that S3, that is our S4. So let me show here. So on this side we have S1, on back side we have S2, on this side we have S3, on back side we have S4, at the top we have S5, and at the bottom we have S6. So these 6 different surfaces we have. So let me simply write their names here. Okay, so S4 on the back side. Okay, so on that side, so it will be A, D, E, O. Okay, S5 at the top of this cube, which is yes, at the top. So it will be D, G, F, E, and at the bottom S5 we have at the bottom S5. So it will be C, B, A, O. Okay, so these 6 different surfaces we have. Then double integration F bar dot n cap ds over S is equal to, obviously, double integration over S1 plus double integration over S2 over S3 over S4 over S5 and over S6. So you can easily guess what I am going to do now. I am going to find a value of that surface integral over S1, then over S2, then over S3, S4, S5, S6, and at the end I will add all these values. So we will have the value of this surface integral. Okay, so we are going to work on it. Make a screenshot of it first, then I will go further. So let us work on S1 first. Okay, S1 you can easily see. So this surface S1, ABGD. So this is surface S1. So this is plane we have, plane which is parallel to the YZ plane and passes through x is equal to A. So its equation is x is equal to A. X is equal to A. So this plane is parallel to YZ plane. So that's why its normal vector n cap. So normal vector for this plane S1 is I, or you can say I cap. So normal vector, you can easily see the x-axis, it's perpendicular. Okay, it's normal to this S1 plane. So the unit vector in the direction of x-axis is I. So that's why n cap will be I cap, right? So it is parallel to YZ plane. So that's why we can easily write dx is equal to dy dz. So here x is fixed, whose value is A, and only y and z are varying. So let us write the limits of y and z. So here y varies from 0 to a, obviously, and z also varies from 0 to a. So both of them are varying from 0 to a, since length of each side of cube is a. So that's why. So then let us find the value. Double integration of f bar dot n cap ds over S1 is equal to, so we got the limits 0 to a, 0 to a. As you know, f bar means f1i plus f2j plus f3k dot n cap. N cap is what? I cap, or simply I you can write, and ds means dy dz I should write. dy dz. So this is equal to integration 0 to a, getting? So f1i plus f2j plus f3k dot. I means I should write I plus 0j plus 0k dy dz. So you know well how to find the value of dot product, right? So this is equal to integration 0 to a, 0 to a. So multiple of I into multiple of I, f1 into 1 we will have f1, f2 into 0, 0, f3 into 0, 0, getting? So that's why we have simply f1 dy dz. So this is equal to integration 0 to a, 0 to a, right? f1. So f1 is a function of three variables x, y and z. So this is I should write x, y, z dy dz. But you know that for this surface S1 the a is fixed whose value is a. So I should write here a, getting? So the value of the first surface integral is this one. So I should work on S2 now, okay? So let me write here, okay, for S2, for surface S2. So first of all we should write equation is, okay. So as you can see S2 is exactly back side of this S1, getting? It's a part of cube. So here we have a S1. So at the back side of S1 we have a S2. So its equation you can easily see it lies in YZ plane. So that's why its equation is x is equal to 0. It lies in YZ plane. So it lies in YZ plane. So again we can write n cap is equal to minus I. I should write minus I because see, let me show you. So suppose it's not a cube, I know that, but suppose consider this is a cube. So here we have a I cap, getting? So normal vector is I cap. So if you are talking about its back side, okay, its back side, so you will have a vector in the same direction, exactly opposite direction. So if you consider I cap here, you should consider minus I cap, okay, exactly opposite direction we have. So that's why n cap is equal to minus. See, it's normal vector in the direction of negative x-axis. So here for S1 we have a normal vector in the direction of positive x-axis, but for S2 we have a unit vector, normal vector in the direction of negative x-axis. So it will be minus I, right? So now ds, so let me write here ds is again dy dz since it lies in yz plane, right? I should write a limits of y and z. So obviously limits of y and z will be same. Y varies from 0 to a and z also varies from 0 to a. Then double integration over S2 f bar dot n cap ds. So I should do the same, getting? I should do the same. Where shall I write? Let me write here 0 to a, 0 to a, okay. So f bar is same, that is f1i plus f2j plus f3k dot n cap is minus I and ds is dy dz, okay. So minus I, so that minus sign will come outside. So that minus I can be expressed in this way, okay. So I'm showing this part, that means necessary changes we have to make here and we will have the same type of answer. So this is equal to, if you take a dot product, multiple of I f1, multiple of I minus 1, so we'll have minus f1. See, there is no j, so its multiple will be 0, 0 into f2 0 and 0 into f3 0. The same thing we will have there, getting? And dy dz. So minus 0 to a, f1, minus sign I took outside. So f1 is a function of x, y, z. So x, y, z and dy dz. But as you know here, for S2 the value of x is 0. You can easily see the value of S2 is 0. So the value of x is 0. So that's why here 0. So this is value of first surface integral. This is value of second surface integral. What is the difference between them? Here we have 0 to a, 0 to a, 0 to a, 0 to a. F1 a yz here, F1 0 yz, getting? And dy dz. It has a plus sign, it has a minus sign. So very small difference we have for S1 and S2. So let us start to work on S3 and S4. So make a screenshot of it, then I will go further. So let us work for S3 now. S3, as you can see here we have a surface S3, B, C, F, G. This is surface S3. See, it is parallel to XZ plane, getting? It's parallel to XZ plane. So first of all I should write equation. So this is parallel to xz plane and passes through y is equal to a. It passes through y is equal to a. So its obviously equation is y is equal to a. N cap, normal vector, getting? See, if you consider a perpendicular vector, normal vector to this plane, it will be in a direction of positive y-axis. So you know well, unit vector in direction of positive y-axis is j. So it will be j, since in the direction of positive y-axis. See, obviously ds is dx dz. See, this plane is parallel to xz plane, so that's why ds will be dx dz. So I should write limits of x and z. So x varies from 0 to a and z also varies from 0 to a. Since see, we have a cube of length of each side is a, so x and z will vary from 0 to a. Then double integration over S3 a bar dot n cap ds is equal to S3. So 0 to a, 0 to a, we have a limits x and z. F bar means f1i plus f2j plus f3k, right? Dot n cap. What is n cap? J only. So j you can write in this way, 0i j plus 0k, and ds means dx dz, right? See, we have n cap is equal to j, but same vector can be expressed in this way. So it will help us to find the dot product. So this is equal to 0 to a, 0 to a, multiple of I into multiple of I 0, multiple of j f2 into 1, here we have f2, and multiple of k f3 into 0, 0, and dx dz. So this is equal to 0 to a, 0 to a, f2. Basically f2 is a function of three variables x, y, z, x, y, z, dx dz. But see here y is fixed, whose value is a, so I should write a here. Okay. So similarly, let me write for remaining surfaces. Similarly, for S3, sorry, for S4, will you guess its value? F bar dot n cap ds. Will you get its value? You remember what was the difference for S1 and S2? The same changes we have to make for S3 and S4. Getting? So for S3 we have got this one. So for S4, see S3 its equation is y is equal to a, but for S4 its equation will be y is equal to 0 since it lies in xz plane. And the second important thing is here the normal vector is j, but for S4 we have exactly opposite direction, so that's why its normal vector will be minus j. So because of that minus sign, here I should write minus sign, okay, for S4. Okay, so it will be minus 0 to a, 0 to a, f2. Here the equation of that surface is y is equal to 0, so I should write x 0 z dx dz. Similarly for S5, a bar dot n cap ds. Will you guess? So S5, as you can see, S5 at the top, okay, we have at the top, and see, it's 0 to a, obviously 0 to a. Here we will have F3. See, for surfaces S1, S2 we got F1, for surfaces S3, S4 we got F2. So obviously for surfaces F5 and S6 we will have F3. So F3, x, y and z will be a. Since its equation is z is equal to a, I should write dx dy. And for S6, f bar dot n cap ds is equal to 0 to a, 0 to a. Here we will have a minus sign, okay, since for S5 our normal vector will be in the direction of negative z axis, so that's why I should write minus, and its equation is z is equal to 0, so we will have z here, 0 here, dx dy. So in this way we got the values of surface integrals for all 6 surfaces. Now simply we have to add them to get the value of required surface integral. So make a screenshot of it, then I will go further. So therefore, the required surface integral is equal to sum of all these surface integrals for all these 6 different surfaces. So now we have the values of all these 6 surface integrals. So let us put all those values here. So the value of first one is 0 to a, sorry, here 0 to a, f1 of a y z dy dz. Okay. So value of second surface integral, there is a minus sign, so that's why 0 to a, 0 to a, f1 of 0 yz dy dz. So value of third surface integral, 0 to a, 0 to a, f2 of x a z dx dz. Value of surface integral over S4, it has a minus sign, so 0 to a, 0 to a, f2 of x 0 z dx dz. So let us talk about S5 and S6. For S5, 0 to a, 0 to a, f3 of x y a dx dy, and for S6 we have a minus sign, so 0 to a, 0 to a, f3 x y 0 dx dy. Okay, so what will we do here? So from first and second integral, tell me what can we take common? We can take dy dz common. So let us do that from, and the integration also we can take common, 0 to a, 0 to a. So in bracket we will have f1 a yz minus f1 0 yz bracket complete dy dz. So tell me from third and fourth integrals, what can we take common? We can take the integration common as well as dx dz. So obviously it will come outside. So 0 to a, 0 to a, f2 x a z minus f2 x 0 z dx dz. Let us do the same for the last two integrals. So this is 0 to a, 0 to a, f3 x y a minus f3 x y 0 dx dy. Okay, so I am calling it as equation number 1. So here we got the value of left hand side, so we got the value of surface integral. So now we have to work on right hand side, that is a volume integral. So make a screenshot of it first, then I will go further. So now let us work on right hand side. So triple integration over V divergence of f bar dv. So here V is a volume of that cube, getting? So this is equal to triple integration. So here we have a cube of length of each side is a. So obviously here x varies from 0 to a, y also varies from 0 to a, and z also varies from 0 to a. I should mention somewhere, because x varies from 0 to a, y also varies from 0 to a, and z also varies from 0 to a. So that's why I could write directly that limit. So divergence means, you know, that del dot, that means I dy by x plus j dy by y plus k dy by z dot. Divergence means what? Del dot f bar. Let me mention here divergence of f bar, which is del dot f bar, right? Okay, so del I wrote here, so value of del is this one, and f bar in a problem, in a statement they have clearly mentioned, this is f1i plus f2j plus f3k and dv. Okay, so I should write dx dy dz. So you know well how to find a dot product, multiple of I into multiple of I plus multiple of j into multiple of j plus multiple of k into multiple of k. I will do the same thing here. So this is 0 to a, 0 to a, 0 to a. We'll have dy by f1 by dy by x plus dy by f2 by dy by y plus dy by f3 by dy by z by taking a product here. So we got dx dy dz. So as you know here, addition is there, we can take separate integration. So I will do 0 to a, 0 to a, 0 to a, dy by f1 by dy by x dx dy dz. Okay, so here for this f dy by f2 by dy by y, I should write 0 to a, 0 to a, 0 to a, dy by f2 by dy by y dy dx dz. See, we can do in this way, we can easily interchange, because here the limits of integration are constants, 0 to a, 0 to a, 0 to a, so we can easily interchange them. So for third also, 0 to a, 0 to a and 0 to a, I should write dy by f3 by dy by z dz dx dy. Okay, so this is equal to 0 to a, 0 to a. What will happen here? The integration with respect to x and derivative with respect to x will get cancelled to each other, and we will have here f1 only. Obviously it is function of x, y, z having limits 0 to a and dy dz plus I will do the same here. Derivative and integration with respect to y will get cancelled. So actually we are using the fundamental theorem of calculus here. So f2 xyz having limits 0 to a dx dz plus 0 to a 0 to a. Derivative and integration with respect to z will get cancelled. So xyz 0 to a dx dy. So let us put upper and lower limits. So 0 to a 0 to a. So integrated with respect to x. So that's why at a place of x I should put upper limit then lower limit. f1 a yz minus f1 0 yz. Okay. So 0 to a 0 to a. So this integration was with respect to y. So at a place of y we have to put upper and lower limit. So f2 x az minus f2 x 0z dx dz. Let us talk about the last integral 0 to a 0 to a. So here integration was with respect to z. So at a place of z I will put upper and lower limit. So this is f3 xya minus f3 xy0 dx dy. So this is equation number 2. So from in 1 and 2, in equation 1 and in equation 2, we have got same right hand side. So that's why we can clearly mention the left hand sides are also equal. So there is no more space to write, make a screenshot of it, then I will go further. So from 1 and 2, okay, so from 1 and 2, we will have double integration over s f bar dot n cap ds is same as triple integration over v divergence of f bar dv. So in this way we proved Gauss divergence theorem for a cubical region. Okay, so make a screenshot of it, then we will stop. Thank you. See you.